Hey everyone, this is Mrs. J, and I've got a lesson here to introduce the idea of logarithms. So I'm going to be starting with the idea of inverses because they lead us right into what a logarithm is. So we're going to review a method called switch and solve for finding an inverse of a function. We're going to start with the one over here on the left, the f of x, and we're going to go through that process. The first thing I have to do is realize that f of x is really the same thing as y, so I'm going to rewrite that. And then you have a two-step process. It's called switch and solve. First thing I'm going to do is switch my x and y. So my y and my x are actually going to switch places. And so what we're going to end up having is x equals, and then it'll be 3y minus 2 all over 5. So I literally just switched the letters around. And then now it's my job to actually solve for the new y that's up here. That's right up there. So what I'm going to do to solve for that is I'm going to start undoing the layers that have kind of been done. The first thing I have to get rid of is that 5. So I have to multiply both sides by 5. 5x equals, and then I have my 3y minus 2. And then I can basically move the 2 over by adding it. So I'll have that on the other side. Oops. And the last step, I just need to get rid of the 3 that's in front. So I'm going to divide. While I do that, I'm also going to put the y over here because that's typically the side we want it on. But if I actually divide both sides by 3, oops, my stylus is acting up. We're going to get the 5x plus 2, and it's all over 3. All right, so this is our inverse, and oftentimes we use an inverse notation so that we can show the relationship that this new function has with the original that was in purple. If the original is f of x, then rather than using a new letter like g of x or h of x, we want to identify this as the inverse, so we actually call it f negative 1 of x. That is the notation that we use for inverses. So our final answer would be 5x plus 2 all over 3, if I can get that written in there with this stylus. All right, so there's our final answer right here in yellow at the end. That is our inverse function, and we use the method called switch and solve. So what I want to do now that's going to help us lead into this new idea is to take a look at this other function over here on the right. G of x equals 2 to the x power. This is an exponential function, and we're very interested in finding its inverse. So we're going to apply the same process as switch and solve. First, I'm going to change this g of x to a y so that I actually have just x and y. And then when I switch the variables, my switch step, I'm going to have x equals, and then it's going to be 2 to the y power. And now, just as before, it's my job to solve for this new y that right now is kind of up in the rafters. It's up here in the exponent. I've got to get that thing by itself. So some ideas that some people might have, we can think about dividing both sides by 2. If I divide by 2, that's some people's first idea. Then they think that maybe we can get y by itself. But if you actually apply properties of exponents, this is 2 to the first. And actually, if you have like bases, you end up having to subtract the exponents. So we'd really get a step like that. Equals x over 2. And you know what? That didn't help us get y by itself. So I'm going to undo that. That's not going to work. Let me make sure I get all that out of the way. All right, so maybe something else you might think to do is to raise both sides to a power to get rid of that. You might think to raise both sides to the 1 over y, which we've talked about. It's raising to the reciprocal. That might get the 2 by itself, and the y's cancel. But over here, you know what? We still have a y up in the exponent, and now it's even more buried because it's in a denominator. So you know what? That doesn't work either. So we could keep trying some algebraic procedures and methods that we might be familiar with in the past, but I'll tell you right now, none of them are going to work. We need something new that we haven't yet seen, and that's where this new idea comes in. So the first thing I want to do is I want to see if you can agree with this statement. What we are trying to say by isolating y is that y is the power, whoa, my screen went funny there, sorry, the power that we raise, I forgot my that, this thing is hard to write with here, hang on, the power that we raise this number 2 to in order to get x is what I want to write, in order to get x. That's what we're trying to say. We just don't really have a way of algebraically saying that yet. So what we've done, the mathematicians way back when they invented this stuff, they said, hey, let's come up with a notation that actually means this sentiment right here. Here, I'm going to circle it actually in green. This right here is what we want to try. And what we do to say that is we actually use this notation. We call it a logarithm, and we abbreviate it with log. And this base number, this 2 right here, that's our base that we're trying to raise to a power, that's in the basement of this log. So it's like in a subscript. So it would be log base 2. And this, in order to get the result that we're trying to get, that's what we're taking the log of. So we get this notation, and the way we say this is it's y equals the log base 2 of x. That's how we read that. And essentially what it's saying is it's y equals the power that we raise 2 to in order to get x. That's what that notation means. So let me flip to my second page. So what is a logarithm actually? If I want you to take anything away from this first video on logarithms, I want you to realize that a log is an exponent. That's all it is. Many people chalk it up to being something pretty challenging, and it can be hard and they don't get it. But really in the end, oops, it's not a plural there. There we go. In the end, a log is an exponent. It's really a way for us to isolate something that is up in the exponent part, and it allows us to rewrite it. So it is very linked to exponential expressions. It's just a way of rewriting them so that we can isolate a different part. Okay? So when you see something like this, log base b of n, and I'm using more general, letters in there, that basically should be read in your mind. You should be thinking it's the power that we raise b to in order to get n. That's essentially what it's saying. So more generally what we say is we have a full expression here. If we're going to use letters in all the spots, we might have a statement that looks like this. Log base b of n equals x. That's going to be true if and only if b, which is down here in the basement, b to this power x equals n. So keep in mind the basement number in orange is your base. The power, because a log is an exponent, the log is equal to x, so x is the exponent. X is the exponent over here. Okay, that's the exponent, and that's b to the x equals n. So this blue n, that's the result you're trying to get. Okay, so one of the first things that we practice as we are learning logarithms is this whole idea of just switching from log to exponential form back and forth. This is what we call log form, and this is called exponential form. Okay, so let's do a couple examples of that. Let's switch the page here. Example 1, we're going to change this log equation, this log expression, into exponential form. So let me switch my colors here. If I'm given log base m of 5 equals x, notice how I'm saying that out loud. I want to switch that to exponential. So the first thing I start with is I look at the base number. That's going to be my base. So I'm going to have m. And remember that a log is an exponent, so this is my exponent. So it's m to the x. And the result is equal to sometimes what I refer to as the of number. Okay? And that's it. That's our answer right there. All right, so in the next one, I'm giving it to you in exponential form, and we oftentimes want to rewrite something like that into log form. This one, I happen to choose one that's actually pure numbers. It's a statement we can hopefully all agree with. 2 to the third is equal to 8. So if I'm going to take that and write it in log form, I start with my log, and it's a base of a number. The base is always your base of the exponent. So 2 is my base. Log base 2. What you're taking the log of is your result. So it's of 8. And what is a log again? It's an exponent. So your exponent is what the log is equal to. It's a way, again, of solving for something that's up in the exponent. 3 is the exponent, and it's equal to the log base 2 of 8. Okay? So that's a little bit about just switching back and forth. Now, if I was just going to give you a log expression, sometimes we actually want to simplify it, and we want to do, if they're in the certain type, then we can do it without a calculator. If you understand what it's saying, oftentimes you can do it with little to no work. But I'm going to show you how to simplify these by just switching them into exponential really quick, and you can see a little bit easier what's happening. Most people in the beginning, when they're looking at a log notation, it's not second nature to really be thinking about which part is which. So switching it to exponential can help. So this first one, log base 2 of 16. Let's say I don't know what it's equal to, so I can set it equal to x. And then basically I'm going to switch it into exponential form. So my base is 2. It's raised to the power of x because my log is the exponent, and it's supposed to be equal to 16. Now, what you should be finding is that this is something we've seen before. This is an exponential equation, and we can get like bases. 2 to the x equals 16. You can actually write 16 as 2 to the 4th. So, if we set those two equal, the bases are already equal now. Therefore, the exponents can be set equal. So, x is 4. So, in the end, log base 2 of 16, if we look at that, log base 2 of 16, we say it's equal to 4. The power we raise 2 to in order to get 16 is 4. And again, if you go back to that concept, a lot of times some of these can be done without the calculator and even without switching. If you know what power you raise that base to get that number, then you can just go for it. Okay, the next example, example 4, has one that might not be as obvious. So it really is the kind that's nice to switch into exponential. So if we set it equal to x and then switch to exponential, I'm going to have 9, which is my base, to the x power equals 27. And once again, this is an exponential equation. It is one where we can get like bases. We do have to change both sides. 9 is the same thing as 3 squared. So 3 squared to the x is 3 to the 2x. And 27 is 3 to the 3rd power. Once you get those like bases, you can then set the exponents equal and continue solving. Okay, so if I divide by 2, I get my final answer here as 3 halves. Oops, there we go. Okay, so again, sometimes you can actually simplify without doing this switch to exponential. Once you get more familiar with logs, you can start looking at things like this and kind of simplifying. For instance, just as a little extra example, if I gave you log base 2 of 8, hopefully you'd recognize, well, hey, 2 to what power gives me 8? That's 3. And you kind of don't need to do the work. If I were to do log base 7 of 49, I would hope that you would know that 7 to what power gives us 49? That would have to be squared, so it's 2. So often if the numbers are nice, you can recognize it. But we always want to have a process to fall back on for when it does not jump out at us. And this whole idea of kind of switching it into an exponential is a good form. Okay? So next lesson, what I'll put together, hopefully, if I have time, is one on solving basic log equations. The x can be in different places, so it's good to remember what to do in each case. And always remember, a log is an exponent, and that will be your best friend as you work with them. Thanks for listening.